Greetings and welcome to this lecture on the World Health Organization Laboratory Biosafety Manual. I have designed and developed this lecture for the purpose of introducing laboratory biorisk managers to the World Health Organization Laboratory Biosafety Manual. Let us explore this manual and decide how we can best apply it to our own respective facilities. At the basis of this particular manual is a recognition that safety and biological safety are very important international issues. And keeping this in mind, the WHO published the first biosafety manual in 1983. And what the manual encourages member states as well as individual laboratories to do is to implement the basic concepts of biological safety for the safe handling of pathogenic microorganisms within your geographical borders. Please take note that the implementation of the recommendations of this particular manual should be done within the scope of your national, federal or state laws. You may also have local regulations which determine your biosafety and biosecurity protocols. The WHO has always emphasized that biorisk management is a collective responsibility. It is not the responsibility of the organization itself, but the responsibility of each of the member states of the World Health Organization. In this lecture, I will introduce you to the World Health Organization Laboratory Biosafety Manual. I will try to facilitate the understanding of the fundamental concepts of biosafety and biosecurity as delineated in the manual. And I will highlight the need for interpretation of the LBM at a regional and national level. Please note that I will be using the acronym LBM to designate the Laboratory Biosafety Manual for the rest of this lecture. And this is what you are expected to be able to do upon completion of this particular lecture module. You should be able to describe the general principles of biosafety, describe the biosafety levels, there are 4 biosafety levels, and adapt the guidelines stated in the manual and develop your own specific laboratory biosafety manual. The reason I have done this is because each laboratory has to develop its own biosafety manual based on the localized conditions as well as on the policy, which is the biosafety policy of the respective institution. To summarize, I will introduce you to the 9 parts of the WHO Laboratory Biosafety Manual. I am trying to do this in order to facilitate your understanding of the manual. It's a very exhaustive document which contains a large number of guidelines, and in this lecture I will highlight specific guidelines. However, you must study the manual in detail in order to obtain guidance for your respective facilities. So there are 9 basic parts to this manual, and the part 1 begins with biosafety guidelines, and we will follow through each part in this lecture. The manual commences with what are termed as general principles. These are general requirements which one needs to adopt for the minimum level of biosecurity or biosafety at your respective facility. There are 4 risk groups which I have discussed in another lecture which you can find on this YouTube channel. These are risk group 1, risk group 2, risk group 3 and risk group 4. Now, risk group 1 is a representation in green. So this is a low individual risk and a low community risk. This represents a moderate individual risk and a low community risk. This is a high individual risk and a low community risk. And this represents a high individual risk as well as the high community risk. Now these risk groups are categorized based on the transmissibility of the pathogen. For example, the risk group 1 will encompass pathogens which are not really lethal in terms of their effect on the human health. So these may cause morbidity, no mortality, and treatment may be available, and the risk of transmission is very low. Risk group 2 pathogens may cause morbidity. However, there is a recourse in terms of the medications or the therapeutic measures which are available, and the community risk of transmission is low. So in this case, this particular individual can be isolated in order to prevent transmission to the community. Now, risk group 3, there is a high likelihood of morbidity as well as a high likelihood of mortality. So this pathogen as well can be contained by isolation of the individual in order to curtail community transmission. And finally, you have risk group 4. Risk group 4 poses a high threat. Okay, so you have a high risk of transmission to the community. And this is the case as with most respiratory viruses. So these are the 4 risk groups, and I've discussed them in detail in my lecture, which can be found on the same YouTube channel. Now, the WHO has categorized 4 biosafety levels: biosafety level 1, 2, 3, and 4. And each biosafety level has its own specific criteria in order to facilitate the design of your protocols for containment. This translates into administrative controls such as standard operating procedures, as well as in the design of your facility in terms of engineering design. Now, from my experience as a biorisk manager, it would be advisable for you to discuss these concepts with your engineering team before you design any biosafety level 1 or 2 or 3 or 4 facility. Okay, and these, in technical terms, we refer to them as containment facilities, although the WHO refers as BSL 1, 2, 3, and 4. In the case of animal containment facilities, you will have the designation A. So this will become ABSL1, ABSL2, ABSL3, and ABSL4. That designates animal containment. And if you have a plus, it means enhanced. So BSL1 plus will refer to the enhanced biosafety level 1. I will explain that to you in the course of this particular lecture. Okay, now most of us will be working at this level, BSL2 and BSL3. This is the basic containment facility. But BSL4 is used in very extraordinary circumstances, as these facilities involve a high level of maintenance as well as the oversight. So most of us are working at these levels, and they accord a suitable amount of a suitable level of containment. Let us look at the biosafety guidelines, which form the first part of the manual. Okay, which come down to what is termed as the code of practice. Now, the code of practice is a term which you need to develop for your own specific institution. So this is the code of practice. So the code is a listing of all the most essential laboratory practices. So these are the practices which form the basic biosafety levels. Okay, and then they will include good microbiological techniques, as well as they can be utilized to develop written practices and procedures for safe laboratory operation. So the first step in establishing a containment facility, or what we term as a biosafety laboratory, is to develop your code of practice. And this has to be done at the level of the management with input from all the stakeholders. Okay, now the WHO specifies what are known as the microbiological risk assessment. This is because a majority of the pathogens comprise microbes. These can be in the form of viruses, fungi, bacteria, and these are microbes. So one needs to address these issues. The first one is the pathogenicity of the microbial agent, the potential outcome of exposure, both in terms of the likelihood of the exposure as well as in the consequence. the natural route of infection. Is it respiratory pathogen? Does it require puncture of the skin, what is known as percutaneous, or other routes of infection resulting from laboratory manipulations? Now, the word laboratory manipulations has been utilized in this particular example because laboratory manipulations in themselves increase the risk of transmission of a particular pathogen. And finally, there's a stability of the biological agent in the environment. This can be noted in the case of many viruses. So some viruses are not stable under normal environmental circumstances. So they get attenuated or weakened in the environment. And this is one of the points which has been highlighted in the WHO Laboratory Biosafety Manual. There are other factors such as the concentration and culture volume of the biological agent. Now, in your laboratory, you may be culturing this biological agent via plates or liquid media. And the concentration and culture volume is one aspect which you need to keep under control. The suitable host. For example, if this particular biological agent or pathogen which you are culturing in your lab does not have access to a suitable host for its transmission, that basically breaks the chain of infection. And you need information from prior animal studies. This can be in the form of research reports, and in order to develop your risk assessment strategy. And finally, you have to focus on laboratory procedures which may increase the risk of exposure. There's another key aspect, which is the genetic manipulation of the organism, and most of diagnostic labs do not work with pathogens that are genetically modified. However, if you are working in a research laboratory, you must look at this gain of function, which I will explain to you in the next few slides, and then the local availability of effective prophylaxis and therapeutic interventions. So if you are working in a country in which you do not have access to proper therapies for the control or containment of the pathogen, please consider the risk of working with that particular biological agent or pathogen. Okay, the code of practice also focuses on containment facilities. So the code of practice should govern the following procedures. Now, these are what are termed as administrative controls. One needs to develop the standard operating procedures to determine access into the facility, to determine the level of personal protection, laboratory procedures, laboratory working areas, biosafety management, laboratory design and facilities, essential biosafety equipment, health and medical surveillance. What this highlights is the need for holistic management of the laboratory in terms of both the physical facilities itself as well as the procedures and the personnel management. And this may also extend to psychological management and in terms of the level of stress which laboratory workers may endure as a result of continuous work in a contained facility. I will briefly describe to you what is expected of a BSL2 or Biosafety Level 2 laboratory. Okay, so let's look at it. I have prepared a graphic for you. So this is a BSL2 laboratory, and as you can see, this is a standard layout. Okay, and what I would like to highlight first is the presence of the autoclave. The autoclave is placed upon entrance on the entry of the door. So all waste is autoclaved here. The next one is the placement of the door. As you can see, the signage is very clearly indicated here. Okay, and then you have your safety showers and your waste bins for radioactive and biological waste or chemical waste, as the case may be. Now, this depends on your specific lab. Are you working with radioactive waste? Then you need to ensure that there is a radioactive disposal container here with the proper precautions such as the thickness of the wall, etc. And as you can see, these are the personnel working over here in the lab. Okay. Now, at the end of this lab is the fume hood. And this is the biological safety cabinet. You will note that these are ducted into the ceiling, and they are hard ducted, and they release their fumes into the external environment. What I want to highlight here is the location of these. So if you are working on the bench with the biological agent, the flow of the direction of the air is this way. It enters into the fume hood and then exits the facility via a HEPA filter. So this accords a certain degree of protection to the laboratory users. The placement of this fume hood is very important. It's located at the end of the lab, far end, and basically everything is drawn into this fume hood and out. There is also over here a biological safety cabinet which has its own ducting. So all the air will be drawn into this cabinet and released into the environment, of course via a HEPA filter, because this accords the secondary level of containment. So that's basically a BSL2 setup which you can adopt to your specific laboratory. Okay, so this is the autoclave, the biological safety cabinet, the fume hood, and we move on to BSL2 now. So what changes in the BSL2? Let us look at it in detail. Okay, the first aspect is the directional airflow. Okay, the BSL3 laboratory is maintained at a negative pressure with reference to the outside air. So which means that the air within the system has to be evacuated, and this forms the principle for directional airflow. Now the air enters through this laboratory and it's discharged via the hard duct, and it also may be discharged via other vents, and it is discharged into the environment via the HEPA filters, which allow or permit the flow of the air but not the flow of the pathogens into the environment, and this accords a level of protection of the environment. Now as you can see, the autoclave has been shifted into the laboratory facility. This will require specific engineering requirements, as the autoclave has to be designed so as to work within this facility, and this may involve an additional heat load on the facility. So that's where engineers come in, and they have to focus on their HVAC, or heating, ventilation, air conditioning and cooling systems. And everything else is basically as in the BSL2 with the disposal containers. However, you will note something at the entrance. This is the vestibule. It can be in the form of an airlock. So ideally, you will have your door with your signage, and for biosecurity reasons, you may have a security protocol in the form of this keypad for signing in or using your thumbprint to access this facility. This is the area in which you change, and then once you change here, you proceed to the negative pressure zone, what is known as a containment zone. So air can only enter into the zone, of course via HEPA filter, and can only exit via HEPA filter. Now if there is a drop in the pressure in this particular zone, we term it as a breach of containment, and we put into place specific protocols to limit the release of the pathogen. This is a basic BSL3 facility. So you have your BIC, your fume hood, your autoclave, and then your double door with secure entry and exit, as I have discussed earlier. Finally, you have your directional airflow, and this is a very important aspect of containment. Now, many biorisk managers ask, do risk groups correlate with biosafety levels? Okay. This is a question which has been posed in many discussions. So if I'm working with a risk group 3 pathogen, should I work in BSL3, or risk group 4 is BSL4? And the answer for this, it depends on your respective administrative controls. You can work with a risk group 2 pathogen in a risk group 2 laboratory and a risk group 3 pathogen in a BSL2 laboratory. However, you must put into place the standard operating procedures and determine the level of risk before you commit to this arrangement. The second part of the WHO Laboratory Biosafety Manual focuses on laboratory biosecurity. Now, biosecurity refers to the intentional release of pathogens and toxins, and this is based on a prior intent, which may be by a state operator or a non-state operator, as the case may be. And we need to put in place the security measures to contain this particular threat. And for the purpose of the discussion in biorisk management, a biorisk term for a pathogen in a biosecurity setting is a biological asset. Okay, let us look at this case. We have a biological asset. In this case, it's a pathogen. And we have internal risks. There can be personnel with an intent to utilize this biological asset for their own nefarious purposes. You also have external risks. Somebody may be aware of the fact that you are working with a pathogen in the laboratory, and they may have an intent to steal that and weaponize it, or as the case may be. And in order to contain both these external and internal risks, we have different measures. One is the physical security, which may be in the form of the inventory. So we have our safe, our freezer is locked. We have different locks and measures such as lighting, CCTVs, and the fencing on your facility. You have physical security in the form of your access cards, which may be fingerprint access. So this constitutes physical security. We also have another layer of security, which is the data security or information security. This may be in the form of checklists, which you maintain on your server. It may be in the form of protocols for the sharing of data, and in the form of protocols for the upload of data to the cloud. These are two aspects which must be considered in terms of a biorisk management strategy. Okay. Now, the internal risks can also be addressed by screening of personnel prior to employment, and this can be done via your local law enforcement agencies. When we work with biosecurity, we focus on the intentional release of the biological agent. What are the likelihoods of that event, and what are the consequences of that event? For example, if I am working with a very high risk pathogen in the laboratory, which is risk group 4, there may be an intent to steal that pathogen and release it into the environment in order to cause social discord, or in order to create an event which is a threat to public health and safety. So there are consequences of that event in terms of its level of its ability to disrupt the local social system, and there is also a likelihood. So this likelihood can be reduced by implementing appropriate biosecurity measures. So you assess the biosecurity risk and you mitigate the risk, both in terms of this intentional release. And finally, you have national standards and national laws, which you must refer to when you consider biosecurity management. So some notes on the implementation of biosecurity management. It should be concurrent with biosafety management. It should be a routine process which forms an integral part of your biorisk management strategy. It should not interfere with ongoing scientific research. This is very critical, as too high a level of containment may confine scientific research. Okay, so we take this note. And transfer of material as well. Materials can be transferred within labs using the proper biosecurity or biosafety protocols. And what one needs to do is maintain the chain of custody, a written chain of custody with documentation, a clear definition of roles, responsibilities, and remedial measures in the case of a breach of containment. And the key aspect is accountability. And this accountability comes in terms of both personnel integrity as well as in terms of the documentation to track the process of manipulation of a biological agent. The next part of the WHO Laboratory Biosafety Manual refers to laboratory equipment. One of the laboratory equipment which has been described in detail is the biological safety cabinet. Biological safety cabinets are designed to protect the operator and the laboratory environment and work material from exposure to infectious aerosols and splashes that may be generated when manipulating materials containing infectious agents such as primary cultures, stocks, and diagnostic specimens. What a biological safety cabinet offers to you is a safe working space. However, in order to utilize a biological safety cabinet, one has to take into account certain precautions such as the administrative controls and standard operating procedures. Okay, this is a class 1 biological safety cabinet. And a class 1 biological safety cabinet is basically a workspace in which you will note the air enters from the outside space and it is exited or exhausted through a HEPA filter into the environment. Now this duct may lead outside the laboratory into the works environment, or in some cases it may lead back into the workspace. However, it is recommended that it lead to the external environment. Now the operator will stand in front of this safety cabinet operating this instrument over here, and he or she will work within the confines of this space. The air circulates within this space, and a major component of the air is exited or exhausted into the external environment via a HEPA filter. This is the basic level of protection to the operator. The class 2 B1 exhausts 70% of the air and recirculates 30% of the air, and the HEPA filter in all cases traps 99.97% of the particles, which is of 0.3 micron in diameter. Now you will ask me, what happens to particles which are smaller in size than 0.3 micron? What you should note that is that a HEPA filter consists of multiple layers of the filtering medium. Okay. So any particle which bypasses the first level will actually get trapped in the second level, and so on and so forth. Secondly, the HEPA filter reduces the velocity of flow of air. So when the velocity of flow of air is reduced, the particles tend to get trapped within the HEPA filter itself. So this is one of the considerations which you need to take into account when you raise that question about the size of the virus or other pathogens and their likelihood of passing through the HEPA filter. Okay, this is how the class 2 B1 filter actually works. So we have the biological agent here, I've indicated as a DNA molecule, and the air is basically drawn through these filters, HEPA filter, and the air which enters onto the top of the bench is actually HEPA filtered, and it exits through this small grill at the bottom, as well as over the specimen or the biological agent itself, and then it's exhausted through the facility via the HEPA filter. Again, the technical term, if it is linked to the external environment, is a hard ducted cabinet. However, if it recycles the air through your facility itself, it is not considered hard ducted. It's allowing the air to filter back into the facility. So this depends on your engineering design. You have to take into account the fact that exhausting large amounts of your filtered air from your facility may result in an increased load on your air conditioning system. This must be discussed with your engineers. Okay, now when you work in a biological safety cabinet, I have set up my cabinet this way. So my pathogen or biological agent is here. This is my area in which I work with the pathogen, and this is my waste bin. Now I will work in this direction. So I will retrieve the specimen here. I will pick up a pipette tip and I will transfer the specimen onto this particular well. Now if you will note here, I have put in absorbent towel in order to absorb any spills. This is a C-fold towel. And I have used double bagging, which I have discussed in another one of my videos on double bagging to dispose of the waste. I am working in this direction. And please note that this is the grill. One must not block this grill, as this grill is permitting a curtain of air to flow around and protecting you from the specimen and the specimen from you. So the biological agent is protected on both sides, and this is critical in diagnostic labs. And the air actually flows through this, so please don't block these grills as well. And the air, there will be a downdraft of air from above. There's a filter on top which creates a downdraft of air onto your workspace. So this ensures that you are safe. Okay, these are some points which you must note. First, your facility must be certified periodically by this specific service provider. So there's a certification procedure. The facility should be located away from drafts of air. There should be no air circulation near the biological safety cabinet. The placement of your material I have discussed here in this particular photograph. The operation should be in accordance with standard operating procedures. For instance, in my facility, I may have a procedure for the decontamination prior to use using ultraviolet light for a duration of 20 minutes, followed by a surface wipe down and a decontamination post usage. And this is stated in the cleaning and sterilization standard operating procedures which accompany this BIC. Finally, there are specific protocols for disinfection in case of a large spill. This section can actually be removed, and then you can clean the area below and disinfect it with a specific agent and with the specific contact time. And finally, there's maintenance schedule. So you have breakdown and periodic maintenance in your SOPs. Okay, we now move on to the next part, which is good microbiological techniques. So good microbiological techniques are an element of biosafety, and these are pertain to laboratory procedures which are listed in your standard operating procedures, contingency plans and emergency procedures in case of a breach of containment, or in the case of, for example, you may have laboratory operators who may get sick in the middle of a procedure and they may have to be evacuated. There has to be an emergency procedure in place for this, as well as large spills and fires, and disinfection of infectious and biological agents using specific agents with the requisite content or the contact time, and finally the transport of biological agents from one facility to another or within the facility itself. Okay, the transport of infectious material is one of the cases in point in which you may require to transport your biological agent from your facility to another state, national or regional, or even maybe a global facility, because you do not have the requisite resources to manage that biological agent in your setting. In that case, one has to resort to transport protocols. So transport protocols reduce the likelihood of that package being damaged or leaking, reduce exposures which can result in possible infection, as your package may travel through the national network of transports including the airline system, and they improve efficiency of package delivery. This is why proper labeling is very important. Okay, these are some of the references. International Air Transport Association, IATA Infectious Substances Shipping Guidelines, and they are updated currently, and you need to refer to the current update in order to obtain the latest guidance. And there is what is known as a basic triple packaging system, which I will discuss in the next slide, and you must ship the consignment along with a spill cleanup procedure. However, this is highly unlikely as the material is triple packaged, but you must still expect or anticipate this possibility of a spill cleanup in the lab or in the aeroplane or in the shipping system. Okay, this is a basic triple packaging. I have made a schematic diagram for you. Now this is the biological agent itself. It's right at the center of this. This is surrounded by your first layer protection, which is waterproof. This can be in the form of a vial, which is a falcon tube, which is, please do not use glass for this unless the biological agent requires transport in glass. Usually we use the polypropylene tubes with airtight locks. Okay. This is in turn surrounded by what is known as an absorbent material. For example, if you are shipping 50 ml of biological agent in a liquid medium, please ensure that your absorbent material can absorb at least 3 times this amount. Minimal. You can absorb, you can put in additional material and padding. However, please ensure that you can absorb. You need to validate this in the laboratory setting in a biological safety cabinet. And then you have your next layer, which is basically your secondary waterproof container. So in case of an impact, this container will crack. However, the internal container is protected. And finally, you have your tertiary packaging, which may be in the form of your box, your cardboard box or your plastic box. And this should all be labeled. This is very important that you use the appropriate labels for this particular package. Label it clearly. If it's going to cross national boundaries, please label it in the language of that particular jurisdiction, or else your labels in English or French or whichever language you have used at the origin may not be deciphered in the country of the recipient. So this needs to be taken into account. We now move on to the next part, which is the introduction to biotechnology. Now, the World Health Organization has recognized the challenge faced by labs in terms of genetic engineering and synthetic biology. So for those of us who are aware, genetic engineering involves the introduction of genes into a specific organism which are beyond the range of transmission of that organism. So in biological systems, we have genes which are transmitted vertically, which means they are transmitted from the parent to the progeny. And we also have genes which are transferred horizontally. This may be from another organism or via genetic engineering. Now, the genes may be introduced with intent to enhance the organism's capabilities. However, there is something which one needs to be aware of, which is called the gain of function experiments. Many national laws do not permit gain of function experiments which increase the virulence of the biological agent or the host range. Okay, so there are some traits which are increased ability to get transmitted. Okay, so for instance, if you have a virus which has a specific type of receptor, a researcher may introduce a new type of receptor which increases its pathogenicity. And these gain of function experiments are good for researchers in terms of the ability to identify threats. However, if these biological agents are stolen, or if there's a breach of containment, there'll be consequences. Okay, so this is one aspect, which is the gain of function aspect. The other aspect is the dual use research of concern, or DURC. This is also a particular area of concern to biorisk managers, as a pathogen which is benign can be utilized for dual use. And this risk assessment must be done in consultation with your national security agencies. Okay, so this is a simple graphic which I've created for you. Let us consider a researcher who's working on viruses isolated from chicken, and he cultures the virus in the laboratory. His assistant introduces new genes into the virus. Of course, their motive is purely scientific research. Now, what happens next is that these genes permit this virus from the chicken to be transmitted into animal hosts. This is purely research-based study. Okay, so they conduct their research. They check the transmission into simian, murine, and bovine hosts. That's what they do. They conduct the test. Okay. Now, there is a breach of containment in this facility, for instance. Okay, we assume that there is a breach of containment. Okay, this is their contained facility with all the precautions, and there is a breach of containment. This may be either as a result of a breach of biosecurity or a biosafety breach. So that's what happens. So then you have your virus, which can now infect humans and cause mortalities. Now the virus has developed or been endowed with the ability to infect human hosts via an animal host. And this is purely because a new gene was introduced. So this is an example of a gain of function experiment. Okay, now in the case of genetic engineering, we focus on the risk assessment, as the risk is very high. And a genetic organism which contains specific traits such as increased virulence must be treated with the highest level of caution. In bio-risk management, we often refer to the iceberg hypothesis, or basically the iceberg concept, in which these are the risks which are visible above the waterline in the case of iceberg, and these are risks which are unknowns. So in the case of GMOs, or genetically modified organisms, there's a high number of unknown risks. Okay? So these can lead to the inadvertent introduction of traits which may convert a benign microorganism into a potential pathogen. We now move on to the next part, which is chemical, electrical, and fire safety. In a conventional laboratory, these are hazards. Chemical, fire, and electrical hazards are always present in any working environment. However, these hazards can lead to accidents. And if you have a fire or a chemical spill and you invite your hazmat team over, or you call a hazmat team to clean up, there's a risk of a breach of containment via the personnel. This is what needs to be taken into account when designing your standard operating procedures for contingencies. So contingencies plan for these particular incidents such as chemical, fire, and electrical safety. So your hazmat teams can identify specific risks, and you can train the first responders in these particular aspects of safety in the context of biological safety. The next part focuses on safety organization and training. So in the safety organization and training, which I've discussed in the laboratory biorisk management system lecture, the role of the biosafety officer is very important, as the biosafety officer is the key element in the entire organization. The biosafety officer may work in coordination with a facility manager. Generally, a biosafety officer is a person or an individual with a background in the life sciences, and the facility manager is an engineer. So they both work in close coordination in order to maintain this facility. And we also have at the peak of this organization the IBC, or the Institutional Biosafety Committee. Now this IBC is basically a committee which focuses on the administration of the facility itself. So you have your IBC at the peak here, and then you have your biosafety officer here, and then you have your laboratory workers, your technicians, and your personnel. I have discussed this in much detail in my other lecture, which is available on YouTube. So at the bottom of this chain of command is your laboratory workers, your laboratory cleaners, your technicians, as well as your researchers and maybe other personnel who are associated with the maintenance of your facility. This is a very important structure, and the roles and responsibilities of each of these components must be established in your laboratory biosafety manual. There's also the safety of support staff, which must be highlighted, as you may have to comply with local occupational safety and health guidelines. And finally, the training. So training is not only conducted at the beginning of a particular experiment. It has to be an ongoing process, because as I mentioned in my earlier lecture on the laboratory management system, training is a part of the continuous quality improvement of your personnel. The WHO Laboratory Biosafety Manual gives us a large number of guidelines on the development of checklists. Now, checklists are basically associated with standard operating procedures. You may be aware of the checklists in a standard, for instance, in an aeroplane, the pilot undergoes a specific set of procedures and then he or she will complete a checklist. Now, this checklist will ensure that a procedure has been carried out, and they improve what is known as situational awareness. Please be aware that working in a containment facility or a biological safety level 3 or 2 laboratory involves a high degree of situational awareness, and this situational awareness is determined by your focus and also your fatigue level and stress levels. For instance, if a laboratory procedure requires you to work for 3 hours, you must be aware of all the situations around you within those 3 hours. And if the biorisk manager decides that 3 hours is too long for a particular procedure, he or she may implement a shift system in which the first laboratory worker works for 2 hours and the next laboratory worker takes off from that. Now, this management of time and work schedules is very important in a containment facility, as fatigue and repetitive tasks can lead to a breach of containment. Okay, so safety checklists will ensure that situational awareness is being maintained. For instance, if I work with a pathogen, okay, the first procedure involves opening the tube. Okay, I check on the checklist. The next procedure involves the opening of the tube and transfer of the medium. Check. So this checklist can be done by yourself, or you can have a buddy observing you and checking the checklist. This checklist will improve the traceability of your process and will enable you to identify any procedures which may lead to potential accidents or incidents. And you also have to comply with standard operating procedures. Please take note that all facilities may or will be audited periodically, and the auditor will definitely require your checklists for examination. Okay, so please maintain your checklists. Ensure that they are stored both in electronic format by scanning the documents as well as in the hard copy or printed format. And they should be filed, and these are controlled documents. Okay, to summarize, the WHO Laboratory Biosafety Manual provides a good foundation for the development of your own institutional biosafety manual. The WHO Laboratory Manual should be adopted within the scope of your national regulations, and regulation and regional adaptations must be made in order to address national, federal, or state laws. Okay, so these are some of the points which I have raised in this particular lecture on the Laboratory Biosafety Manual, and it is a good starting point to reference this WHO manual, as it will provide you with the basic requirements for establishment of biosafety at your respective facility. Which brings us back to the key point, which is biosafety and biosecurity are both collective responsibilities of individual laboratories as well as member states of the WHO. Please ensure that your laboratory is maintained according to the national and international requirements for biosafety. These are some of the references. So I have this, the primary reference is WHO. The secondary reference is the BMBL. This is a very good reference in which various procedures are described. This is the CWA, SAN Workshop Agreement, CWA 15793. You can refer this in order to determine your laboratory biosafety protocols and to derive new protocols, standard operating procedures, and management structures. And this is a very useful reference, which is the pathogen safety data sheet from the Canadian government. This allows you to basically identify the risk group by searching through their website. So this allows you to determine which is the risk group, what are the particular precautions, as well as other reference material. Okay, so risk group 1 to 4, as I mentioned earlier. Okay, that brings us to the end of this lecture. Thank you very much for watching this lecture, and please participate by clicking on the links to other lectures in this particular playlist. I hope this lecture has been informative. Thank you very much, and stay biosafe.